Greetings and welcome to a new video about an induction motor example. This is example number 3. In the example we will discuss another problem. So let's look at our problem. We have a 4-pole 440 volts RMS 60 Hz 3-phase, but this time a delta connected induction motor which has the following parameters: the RS and the XS for our stator part, and we have the RR prime and also the XR prime for our reflected rotor parameters, and we have the magnetization losses as a value of 40 ohms for our reactance. What we want to calculate is the line current for this situation, the power factor, the output power, the output torque, and the total copper losses, which is then the summation of the losses due to the stator and also the rotor, and the efficiency as a final calculation. So let's look at our calculation step by step. Before we move on, of course, we always start with our model for our induction motor. And for the line current, the first one, we know it is related to also the phase current. Since this is a delta connected system, the delta connected induction motor, the phase current will be different than the line current. So we need to also consider that one. And we have here also the phase voltage. So before we move on, of course, we need to also calculate the impedance, which is actually seen here across these two elements. So this is our phase voltage and this is the phase current, but this is the impedance we need to calculate here before we move on. So the impedance seen here is the series resistance of this series combination of this resistor, the reactance of this inductor, and also the parallel combination of these two branches, which is actually shown here. And I have taken now these two resistors, RR prime and also this load together, and that is also equal to RR prime over the slip value S. And we can of course rewrite this such that we have this condition, but we know that we require the slip. The other parameters we know from this information from the exercise. So how do we calculate slip? Before we do that, we need to go to the synchronous speed, which is then given by this expression. Synchronous speed in radians per second is equal to 2 over the number of poles times the electrical speed. In this case, the electrical speed is given by 60 Hertz here, so we need to convert that also in radians and then just substitute the values given here. So 4 pole 60 Hertz, and you will get 188.5 radians per second approximately, and that's exactly equal to 1800 RPM. Alright, so we can now move on to the slip. The slip is related to the synchronous speed and also the rotation speed, so the rotor speed. We have now this and these two values, so we can just substitute the values we have. Of course, we can also do that in the RPM values. And then we have the following result, 1 over 36. Okay, now we have the necessary information to calculate our total impedance. Then we can just substitute the given values in this exercise. And we have this situation, simplifying this part, which is then just 18, and then simplifying further. And if you take another step, you will have then this straightforward expression. We can now combine the real and the imaginary parts together. Then we have 15.7 plus J 9.12. If I now also convert this to the polar expression, you can see the magnitude and also the phase. This is important in this configuration because we need to divide this by, we need to of course have this in the denominator of this expression. So we need to have it in the polar expression to work it out easily. Okay. For the next step, we need to of course also know what the phase voltage is. Now for the delta connected system or delta connected motor, the phase voltage is equal to the line voltage. So this is line voltage, always line voltage, configuration. But the phase voltage is now then also 440 volts RMS. So we can say line voltage is equal to the phase voltage is equal to the 440 volt RMS. So we can also say this voltage here, the voltage source here in our per phase model, we can also say that it's 440 volts with a phase contribution of 0 degrees. Okay, well we have then the following, just substitute the values, of course now using the Vs in our circuit model. we have 440 volts over 18.2 the magnitude, and also the phases, you will get 24.2 with a phase contribution of minus 30 degrees amperes in RMS. Okay, we are now very close because we have now the phase current, but we need of course the line current, and there is a relationship between the phase and line current. For the delta connected motor, the line current is square root of 3 times the phase current, so it is square root of 3 times larger. So then the magnitude of the line current will be then this. So line current is square root of 3 times the phase current in magnitudes. So if you now just substitute the values here, you will get 41.9 amperes RMS. Alright, that's for the line current. Now, the next one is the power factor. The power factor is defined as the cosine of this angle of this total impedance. So, the cosine of this theta. And in this case, if I look at the expression for our total impedance, the theta is here 30 degrees. So, theta is 30 degrees. If I now substitute the value here for the theta in the expression for the power factor, you will get 0.866, and this is lagging since the theta here is positive. You can also see it in a different way. If you look at the angle by the current of the phase, so the phase current, that is minus 30 degrees, and if this is a minus, that is also another way to look at it, that this is a lagging. If this was a positive for the current, the phase, then it was a leading power factor, but then this was of course a negative. So it is actually the reverse of what you see in the current. Alright, let's move on to the next step, which is the output power, P out. That's defined as the developed power minus the rotational losses in our system. We know the rotational power loss, which is 1 kilowatts in this configuration for this operation of 1750 RPMs. Okay, we need of course the developed power, which is then given by this expression, again 3 times the I squared R expressions, like that, because this is a 3-phase, we need to multiply the expression of I squared R by 3. So we need to have this current also, which is actually flowing in this branch through this load also. Now, before we move on with that one, we need to of course use the per phase current for this. So we have a current divider rule. So what we want is of course the current here, which will of course split in 2 branches, but we know this, and we can now use the current divider rule, which is then given by this expression. So this current, which is flowing in this branch, is equal to the other reactance or other impedance, which is actually shown here, divided by the total impedance in this branch together, which is actually shown here. And again, I have taken these 2 resistors, R prime, and also the load together, which is this expression, and that you multiply this by the source of this node, which is just IS. So if I now just substitute the values here, we know already the IS, and we also know these values from the information here, and also the slip we have determined already. Then we can simplify this using the values here, and we have now the next step is then 21.8 amps in RMS, and with a phase contribution of minus 60 degrees. So we have now the necessary information for our PD, which is then the developed power. So the developed power will be then just using this formula again. You substitute the value, of course you take the magnitude of the IR prime and our slip value, and also the resistor value of R prime here, which is then 0.5. You can see that in the information here. Now you will get 24.95 kilowatts. Now we are now very close to the P out. P out will be then the developed power minus the rotational power loss, which is just what we have here, minus 1000. You will get then 23.95 kilowatts. The next one is the output torque. Output torque is related to the output power and the rotational speed, which is then of course given here, what we needed in the radians per second. So we need to convert this using the formula. This is in RPM, this is in radians per second. We have this, so we can just calculate this using this formula, and we have now 183.3 radians per second. Now you do the math here for yourself, just substitute the value of this power out, and also what we had just calculated for our rotor speed, then we have 131 Newton meters. That's for the output torque. So moving on to the next one is the total copper losses. So we lose some power due to the copper losses, and we have of course the stator and the rotor together. So the stator power losses, stator copper power losses, and also the rotor copper power losses. Now let's look at it by one. So we have the stator copper losses, which is then given by this expression, again 3 times, and again I squared R expression, as you can see here. And we need this current here, and also this resistor value, and multiply it by 3. So we need this current, which is 24.2 amps in RMS. We just calculated that, of course. Now we can just substitute the values, and also 1.4, which is given here in the information. We get 2.11 approximately kilowatts, or 2108 kilowatts for our stator copper losses. The rotor copper losses, PR, again in a similar form, again 3 times, but this time we of course look at this branch, and we have this current IR prime, and we look at this resistor, which is then what we have here. So if you now just again use the current value for that part, which is 21.8 amperes in RMS, then we have the result here, which is then 713 watts. Now we can now combine these together. We have now these two values, and then the summation of this one is 2821 watts. That is our power loss due to the copper in the stator and also the rotor. The next one is the efficiency. But let's first check what we have now so far, because we want to also check the input power. The input power is given by the developed power and the power losses due to the stator, so actually the copper, and also the rotor copper losses here. So we just add them up and check also the result using this formula, which is also valid for a 3-phase system. Again, here the Vs is the phase voltage and the Is is the phase current, both in RMS. Now we know these 3 values just calculated here, so just substitute here what you have, and also what we have from our information of the problem, 440 volts. This is of course a line current, but for the delta system, delta connected induction motor, the line current will be also the phase current. And this is 24.2, which is Is, this is the phase current, already seen here. And we have also the theta, which is then the phase of the total impedance ZS. Now if I now calculate this, the left side, I will get 27.77 kilowatts, and for the right hand side I will get 27.66 kilowatts. So it's very close to each other, so it's just the very small difference due to the rounding of errors. So we can say we have checked this and it's correct. Now finally the efficiency. The efficiency is always defined by the output power divided by the input power. So we have this result, so we have the output power, I mean this one, 23.95 kilowatts, and we have the input power, we have now here 27.77 kilowatts. So this is already calculated in the previous discussion. Now we have now just worked it out, you will get 0.862 or 86.2%. That's what you have for the efficiency. Let's summarize what we have so far. And in total, summary of the results: parameter, the line current, the power factor, the output torque, so going on by one, the stator and the rotor copper losses, I've just made them here separately, but the total is of course what we have here. You have also the output power, and you have also the efficiency. So the output power was 23.95 kilowatts, the efficiency is already calculated, and the rest of the values are also shown here as a summary. This concludes this example about another induction motor, but this time it is delta connected, because we have also discussed the Y connected system, Y connected induction motor, and to have also a different discussion, in this example we have discussed also in great detail the delta connected induction motor, and we have used the equivalent circuit to work out the necessary calculations. If you have any questions or comments about this exercise, please let me know and I will try to answer them as soon as possible. See you next time and take care.